Hello and welcome to Sunday's edition of Cracking the Cryptic, where I'm smiling because I've just opened this puzzle, which is the one the testers have recommended for me to try today. And if there was ever a puzzle that looked more Fistomaphelian, let's describe it as that. I struggle to think of that puzzle in my mind. It's sort of a Mahjong type situation. We've got like Mahjong pieces in the corners, and the 2x2s in the corners, and something that seems to overlap very precisely with the Fistomaphile ring around box 5. And this puzzle is called Overlap, and it's by Blackjack Fitz, and apparently it's rather wonderful. So this is what we're going to have a go at today. And in fact, I don't have much news for you. Let me just think. No, I really don't think I do. So just an appeal as always, if you do enjoy the channel, please consider subscribing. We'd really appreciate it. And you can even check us out over on Patreon, where we have our Sudoku Club, a go-go, where there's all sorts of extra content every month, including, of course, our Sudoku hunts. But yeah, that's all the news. So why don't we just get on straight with the rules of the puzzle and see what Blackjack... I have done a Blackjack Fitz puzzle before, actually, and it was very good. And I don't think it was very easy. Gosh, it feels like it was a few weeks ago. I can't remember exactly what it was, but I'm sure I've done one because I reckon. Oh, yeah. It's coming back to me because I remember that I wished Blackjack Fitz a happy birthday, and then the following day I did the puzzle. Oh, now can I dredge up from my mind what that puzzle was about? Of course I won't be able to now. That's going to infuriate me. Oh, that is going to be like one of those earworms that nags away. Anyway, I can't remember, but I remember liking it. Anyway, the rules of this one are as follows. Given digits today as well. Normal Sudoku rules apply, so we've got to put the digits 1 to 9 once each in every row, in every column, and in every 3x3 box. Digits cannot repeat on the marked diagonals, so on this diagonal here, we're going to have the digits 1 to 9 once each, and on this diagonal we're going to have the digits 1 to 9 once each. And digits along a purple line form a consecutive set of non-repeating digits that can appear in any order. So let's look at this line here. They do overlap, don't they? It's going to be confusing. Imagine this square was a 1. Well, then we would know that because this sort of L pentomino has to contain a set of consecutive digits without a repeated digit, these would have to be the digits 1, 2, 3, 4, and 5. And they can be in any order. So in fact, that would have to be 2 because it couldn't be 3, 4, or 5. This could be 5, say. That could be 3, and that could be 4. I mean, I might have got something wrong there in terms of Sudoku, but that, I think, is a conceivable way to fill this line if that square was a 1. Do have a go. The way to play, as always, on Cracking the Cryptic is to click the link under the video in the video description, and that will take you to a page that looks exactly like this one, where you can play the puzzle on whichever device takes your fancy. But now, I get to play. Let's get cracking. I mean, I think probably today I have to prove Fistomaphile first up. I can't believe this puzzle isn't Fistomaphilian, so I'm just going to do that. So there is a theorem in Sudoku that will prove that those 16 cells there are the identical 16 digits that will appear in those 2x2s in the corner. And there is a proof of that that's very simple. I did it on Numberphile, actually, a few months back. But that proof runs as follows. What we do to start with is we highlight those cells in the grid. Now, these green cells, we can describe the contents of these green cells absolutely exactly, because we know that this row altogether has one set of the digits 1 to 9 in it. And so does this row, and so does this box, and so does this box. That's just the rules of Sudoku. So the green cells altogether have 4 1s in them, 4 2s, because the green cells are 4 sets of the digits 1 to 9. The green cells altogether must have 4 1s, 4 2s, 4 3s, all the way through to 4 9s. Now, let's instead highlight some other cells. I'm going to, let's make those orange. Oh, that's horrible. That's a horrible, horrible colour choice. Maybe blue is a decent colour choice. I'll make them blue. Now, can we describe the contents of the blue cells? Well, yeah, we can, because each of these columns is one set of the digits 1 to 9, and there are 4 of them. So the blue cells altogether contain 4 1s, 4 2s, 4 3s, etc., all the way through to 4 9s. In other words, the contents of the green cells and the blue cells are at this point the same. Now that's crucial, because imagine that we removed this cell from both the green and the blue sets. Well, how many cells have we now got left in blue and green? Well, in blue we had 36 cells, we've now got 35. In green we had 36 cells, we've now got 35. And although we knew the exact contents of green and blue before we removed this cell from both blue and green, we don't now know the exact composition of blue and green because we don't know what's in this square in the final grid. But we do know that if we've removed this cell's contents from both the green set and the blue set, given that green and blue were exactly equal before, they must still be exactly equal. So if we compare the contents of green and blue, they're still going to be the same, because they were the same before we took this digit out, and we've taken this digit out of both, or this cell out of both. And we can obviously repeat that for any cell that has green and blue shading in it. And there you go. We reach a position where we're just left with 16 cells in green, and they must be the same as the 16 cells in blue. And that will work for any Sudoku you like. It's weird, isn't it? But it is true. There is an extension to that rule as well that applies in diagonal Sudoku. I don't know if that will be relevant. The extension says that if there is a digit that is, if there is any digit that is not in the green ring, then that digit goes in the middle of the puzzle. And that digit, and there could only be one such digit. So in fact, we know that there is the only digit that couldn't be in the green ring now. Ah, but hang on, that's total nonsense. Right, that's not relevant to this puzzle, because there must be a 5 in the green ring, and that's because there are these 5-cell sequences in the green ring. And one thing, if you think about a set of 5 consecutive digits from the digits 1 to 9, it doesn't matter whether you start with 1 or start with 9, you're always going to pick up the 5 in the middle. So there's 5s on all of these. But I mean, they could be in the overlapping period in position like that one. But every one of these L-shaped pentominos has a 5 on it. And that 5 is never in the corners because of the diagonal. So there's a 5 in one of these, a 5 in one of these, a 5 in one of these, and a 5 in one of these. So that's a tiny deduction. There's no 5s in the same row and column as the existing 5. So now we've got, as Maverick flies over, we know that there are no, we don't. I was about to say we know there are 4 5s in the blue cells, but we don't. Do we know that or not? Actually, have I already made a mistake is now what I'm wondering about. I have, haven't I? I've made a logical... There is a logical flaw in what I've done here. So what I did was this. I said that there must be a 5 on each of these L pentominos, and that is true. And I extrapolated from that to say, well, because there's no 5 in the corner, because of the diagonals, there must be a 5 in one of those, there must be a 5 in one of those, there must be a 5 in one of those, and there must be a 5 in one of those. But that's not true. Because imagine that was a 5. Well, that has fulfilled my obligation to place a 5 on this pentomino and on this pentomino. So that wouldn't require me to have a 5 necessarily in one of those 3 squares. Oh, that's very confusing. Right. Okay, sorry, I don't really know how to pencil. I mean, I know there are some 5s in the green ring, but I'm not sure how to pencil mark them. And any 5... Oh, wait a minute. There's a problem here. Wow. Wow. Okay, no, I'm going to I've totally changed my mind about how to do this puzzle. Okay, let me explain what I'm thinking. So a few minutes ago I said I wasn't going to explain, or I didn't think it was relevant, that there is this theorem, extension of the basic Fistmerfeld theorem, that occurs in a diagonal Sudoku. And that theorem states that if there is a digit that is not in the green ring, that digit must go in the centre of the puzzle. And there could only be one such digit. And then I spotted that each of these pentominos had to have a 5 on, so I immediately put that to one side in my brain. But, what that means is, because there is a 5 in green, there is one of every digit, at least one of every digit in the green ring. And I can show you why that's true, but it's also very, very important, I think, because these Mahjong pieces on the side of the grid, well, one thing I've noticed is there's a square. You see there's an internal square. So where I got to in my brain as I was looking at this was, okay, well, can I put 5s into all of these 2x2s in the corners? And I'm going to claim now the answer to that is most certainly no. Because if I did, this sequence, well, none of these blue sequences, because they're consecutive digits, one of which is a 5, and they're 4 cells long, because that's how many vertices there are. Well, that's how many cells there are in the 2x2s in the corners. There could never be a 1 or a 9 in the blue cells. But if there can't be a 1 or a 9 in the blue cells, there is not a 1 or a 9 in the green cells, and that digit should simultaneously go in the middle of the puzzle, where it most definitely cannot. So, there's a problem here that with the number of 5s that we can put in the corners. Right. So let's prove the proposition that says, okay, if there is a digit that is not in green, it must go in the middle. And the way to prove that is to say, okay, well, let's imagine there was such a digit. Where would that go in box 1? Well, if it's not in green, by Fistmerfeld we know it's not in blue. So it would be in one of those cells, wouldn't it? That would. And where would it go in this box? Well, again, it would be in one of these, and one of these in boxes 1, 3, 7 and 9. Now, we don't know where it would be in these, but the key thing to realise is, let's say it was in one of these 2 cells. Well, then we could propagate that round the grid, because if it was in one of those 2, it would have to be in these 2. It would have to be in these 2, and it would have to be in these 2. Now, the only other thing that could have occurred is it was one of these 2 originally, in which case it would be propagated into the yellow dominoes instead. But the crucial thing to realise is that in box 1 and 9, and in boxes 3 and 7, there is no way that a digit that is not on the Fistmerfeld ring appears on the diagonal. It can't be on the diagonal. So when does it ever appear on the diagonal? It must be on the diagonal somewhere, mustn't it? So that digit, if it's in orange, is going to... well, it doesn't matter whether it's orange or yellow. It's got to be in one of those squares on the negative diagonal, and it's got to be on one of those squares on the positive diagonal. So to appear on the diagonal and meet the criteria, it's got to be in one of those 3 and one of those 3. It must be there. That's absolutely forced. So there couldn't be 2 such digits that weren't in the ring, because they both have to be there. And now in this puzzle we know that there is a 5 in the middle. And we know there is a 5 in the green cells. So actually there is no digit. It's impossible for there to be a digit that is not in green in this puzzle. And that means, let's keep going with the theory, that means that there is a 1 somewhere in this green ring. There is a 9 somewhere in this green ring. And that means in the Mahjong pieces, somewhere there's a 1 and somewhere there's a 9, and they're 4-cell sequences. So 1, 2, 3, 4, 9, 8, 7, 6. So there cannot be more than 2 5s in the ring, and yet there are 4 5-cell. There are 4 5-cell pentominoes. So so they must appear at the overlaps, mustn't they? Hang on. I can't put more than 2 5s in these green cells. It's impossible to do that. Because if I do that, I've got to have 3 5s in the Mahjong pieces, and I couldn't have a 1, 2, 3, 4 sequence, as well as a 9, 8, 7, 6 sequence, which I must have. So there's a maximum of two 5s in green. So if that was a 5, I'm trying not to sneeze. If that was a 5, I would have fulfilled the obligation to have 5 on this pentomino and on this pentomino, but I would need to have a 5 on this pentomino and this pentomino, only with 1 5, so it would be there, right? So the 5s are either in those 2 positions exactly, or they're in these 2 positions exactly, but there are only 2 of them. And they must be either in orange or in yellow. This is fascinating, actually. This is really very interesting. So what does that mean for the contents of the Mahjong pieces? We know there must be. There can only be 1 1. Because there must be 2 5s in green. Therefore, there must be 2 5s in the Mahjong pieces. Therefore, those 2 Mahjong pieces with 5 on can't get to 1 or 9. They could only be something like 2, 3, 4, 5. Or 5, 6, 7, 8. So there's 1 1 in the Fisternfell ring, and there's 1 1 in the Mahjong pieces. So one of the, I'm just going to make this as an aide-memoire, one of the Mahjong pieces is 1, 2, 3, 4. One of them is 6, 7, 8, 9. 2 of them have 5 on, but I don't know what else they have on them. But we have got a given 1 here. Does that mean these can't be 1, 2, 3, 4? Don't see why. I'm just trying to understand what the outside of the Mahjong pieces means. These sort of triominoes. So there's 2 digits common to the triominoes. Yes, okay, so the corners of the triominoes must be extreme within the sequence. That makes sense, doesn't it? Yeah, that must be right. So if this was a sequence 1, 2, 3, and 4, I think those squares have to be 1 and 4. That's where my brain is taking me. Now let's try and prove that. If this was a 2, could this be ever correct? Well, these 2 digits now, this has to be a sequence, so these 2 squares have to include a 3. And either a 1 or a 4. So let's say it was 1. Now this would be a 4. And this is not a sequence on the other side. Yeah, it can't work, can it? So if we do it the other way around, this would be a 1. Yeah, so that does make sense. There must be... Yeah, is there another way of me describing that? There probably is. Yeah, there is. So if we look at the sequence of digits 1, 2, 3, and 4, and we say, okay, I need to split that into 2 different 3-cell sequences. There are actually only 2 options, aren't there? There must be a 1, 2, 3 option and a 2, 3, 4 option. So those are the 2 sequences, and the common digits between those 2 sequences must be in the overlapping cells, which are the 2 and the 3. So that's a more rigorous way of proving that. Right, so that means this one, wherever it lives, will have a 2, 3 here and a 1, 4 here. So if this was 1, 4, we'd know that was a 1. We'd know that was a 4. We know this was a 2, 3. And actually we know the order from the 3 here. That's interesting. So this one, which is 6, 7, 8, 9, wherever that lives, that has 7 and 8 on the diagonal. And then we've got 2 sequences that involve 5. Sorry, it got called away. Happens more at the weekend. In fact, I should have shut my door and forgot. So we might get interrupted again. I'm sorry. I have stepped away for a few minutes as well there. So let me just see what we were doing. I mean, I've not even sniffed a digit yet, have I? So I can't really say that I was making stellar progress, but we were... Oh yeah, okay. We'd worked out that the sequences... Yeah, that the sequences in the Mahjong pieces had the sort of internal digits, yeah, because if you have like 1, 2, 3, 4, we've got to have 1, 2, 3 sequence and a 2, 3, 4 sequence, and a 2, 3 are common. Right. Okay, and we've got 2 5 sequences to come in the Mahjong pieces. And the 5s can't be on the diagonals because of the middle. So the 5s are going to be in the edges, wherever they live. So, right. Okay, so we can make one more fairly straightforward deduction from that, can't we? I think. Because, yeah, just to illustrate this with the 1, 4 again, what we're saying is that if this was the 1, 2, 3, 4 sequence, the 1 and the... Oh, whoopsie. The 1 and the 4 would have to be there. The 2 and the 3 would have to be like this. So that's one possible way this could work. But you'll notice that in doing that, it was the extreme digits of the sequence that were on this diagonal, that weren't on the line. So now because we know that there must be 2 5s in the ring, then the 5s that live that are not in the Mahjong pieces, that are the 1, 2, 3, 4, and the 6, 7, 8, 9, the 5, so let's say it's this one, for example. If we know there's a 5 on here, we know the 5 is not there. So the 5 is in one of those 2 squares, which means it's extreme within the sequence in this 2 by 2. So that means that there is a... That means that the 5 is extreme, so it must be with a 2 or with an 8. So it's either 2, 5 or it's 5, 8 there. But... And the same is going to be true for another 5 that lives somewhere else in the Mahjong pieces. So... But how do we know which is which? So, I mean, what I'm thinking there is, say this one was 2, 3, 4, 5. I feel like this one would have to be the other, just because of how symmetrical this grid is. But why couldn't that also be 2, 3, 4, 5? Yeah, no, I can see why, actually. Okay, that's fine. right, this is actually very clever. It's really clever. So the reason this is not possible is, imagine that this was the situation, because we know that if we do have a 2, 3, 4, 5, well, no, that was a poor way that I was going to phrase the logic there. But let's imagine that we do have 2, 2, 3, 4, 5s. The key thing there is to realise that those 3 sequences all have 3 internal to the sequence. And that's going to mean that there's going to be 3 of these Mahjong pieces with 3 on the diagonals. And there can't be 3 Mahjong pieces with 3 on the diagonals, because those diagonals inevitably will involve a clash with the 3s. So that cannot be true. It cannot be true. But we know that there are. So I think this proves it, doesn't it? Because we're saying that if one of them is 2, 3, 4, 5 now, the other must be, because 5 is extreme within the sequence, the other must be 5, 6, 7, 8. But we can disprove 2 sequences which are both 5, 6, 7, 8 in exactly the same way that we just disproved that there were 2 sequences that were 2, 3, 4, 5. Because here we've got double 7. 7 is internal to that sequence, and 7 is internal to this sequence. So there would be 3 7s on diagonals, which can't work. That's gorgeous. That is so clever. So now we know that there is a definite... let's put the little one at the top. There's a definite 2, 3, 4, 5. There's a definite 5, 6, 7, 8. And, well, now we've got to be a bit careful as well, because the internal digits, there's definitely 2 3s that are internal digits, and there's definitely still two 7s that are internal digits. So they can't go opposite one another, can they? So let's say this one was 6, 7, 8, 9. If that was 6, 7, 8, 9, there would be a 7, 8 on the diagonal. So this one couldn't be this one. So I don't know what that means quite. I think it means something. Does it mean something to do with the 3 there? Maybe. It means that it's not possible for both of these to be the sequence that has an internal 3 on it, because that internal 3 would go in those 2 positions. So okay, I can't quite see this. Bobbins McBobbins face. Okay, let's do it differently then. Yeah, okay, so here's a different way of thinking about it. Because we know, let's look at these 2. Let's focus on those 2. Well, these have an internal 3 on their sequence. So these cannot be opposite corners of the Mahjong. So if this was one of these purple sequences, the other purple sequence could not go opposite it in the grid, because that's going to put 2 3s on the diagonal. So that's definitely not right. But that does mean that these are horizontal or vertical sequences, aren't they? So the 2 purple sequences, because they can't be on opposite diagonals, are going to sit in that sort of arrangement, or this sort of arrangement. But look, there's loads of digits in common between these 2 sequences. 2s, 3s and 4s are in common. And that means that however we orientate, well, what it means simply is that those 2 are not the 2 purple sequences, because they would have to be those would have to be 2, 3, 4 by Sudoku, and that cannot be true. And that means, well, actually the same is true here, because there's a 4 here, so this can't be 2, 3, 4. Right, so what we know now, because purple sequences can't be vertical Mahjongs, they're horizontal Mahjongs, because they're not diagonal Mahjongs. Ah, that's so annoying. So we don't know. Either this is 2, 3, 4 or this is 2, 3, 4. One of those things is true. Yeah, okay. Okay, but right, this is a seriously clever puzzle, because now let's turn our attention to the other two sequences then. Let's make those something red. Now, because we know that the purple sequences are in horizontal Mahjong tiles, the red sequences are in horizontal Mahjong tiles, and they have 6, 7 and 8 in common. So if we were to make the red tiles there and there, 6, 7 and 8 in row 7 would go into those squares and clash here. That doesn't work. And that means that these Mahjong tiles are the red tiles. So these squares are from 5, 6, 7, 8 and 9. And this is a 6, 7, 8 sequence. And these down at the bottom are 1, 2, 3, 4 and 5 Mahjong tiles. And this is a 2, 3, 4 sequence. And now, where do the 5s go in the Numberphile ring? Not in the yellows, after all. So they must go in the oranges. This is mesmerisingly clever. It's ridiculous. These are not 3s. But 3... Yeah, 3's always on the diagonal, so that's a 3. Because 3 is always internal to its sequence. So 3 is in one of... Whoa, 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 whoa. 3 is in one of those squares. It's not there, is it? Because the 3 in this sequence is internal. Yeah, okay, where is the 3? In fact, that gives me a 3 in the corner. For nothing. I didn't even do anything and I get a 3 in the corner. Because the 3 on this sequence, I don't know whether this sequence is 1, 2, 3, 4 or 2, 3, 4, 5, but the 3 is on the diagonal because it's internal to the sequence. And it can't be there. So it is there. And that's 3 in the corner. That's 3 in the spotlight, losing its religion. These are not 4s. Does that do it? Hang on. 1 and 5 are very extreme on the sequence. They can't be internal to any sequence, so that's got to be a 2. These have got to be a 1-4 pair. Sorry, that's totally obvious. I didn't see it. So if this is the 1, 2, 3, 4, that's that one. So this is the 2, 3, 4, 5. So there's no 1 on this one. The 2 and the 5 are extreme in the sequence. So there's a 4 on the diagonal here. That 4 does the 4 and the 1. The 2 and the 5. This is just filling itself in. This is quite ridiculous. That's a 5. Is that true? No, that's not true. It's not. I mean, it's true if there is a 5 on this sequence, but there needn't be because we're in the red sequences, and this could be 6, 7, 8, 9. Sorry, I just didn't spot that. 4 is in one of those squares because it can't be here because of the diagonal. That square, this square here, look, it has to be in a consecutive sequence with 2, 3, 4 and 5, so that's 1 or 6. Where are 3 and 4 in the middle box? Ah, I don't know. Where's 3 in the middle box? 3 is in one of those squares because this diagonal 3 knocks those off. So 3 is not here. Maverick flying over again. Okay. So can I know these are not 5s. So 7. Okay, so 7. I always know 7 is internal to a red sequence, so I can get rid of 7s from those squares. There's definitely a 7 in one of these. There's definitely a 7 in one of these. So 7 in the middle box is in one of those squares. That doesn't do anything. I'm going to have to be careful with these soon because obviously these are nothing to do with the Sudoku. Insert in box 2. This square is consecutive with 5, 6, 7 or 8. So that is 4 or... Oh, hang on, it's not 4. There's a 4 on that diagonal. This square is 9. It's the only thing it can be. That's great. So that knocks 9 out of these. And now we can work out what this sequence is. This is 5, 6, 7, and 8. So these are a 6, 7 pair. This is a 5, 8 pair. And, well, we now know what this sequence is then. So this is the 6, 7, 8. This doesn't have a 5 on it. So this is the 6, 7, 8, 9 sequence. So we can, at least we know there's 6 and 9. We know these are 7 and 8. Let's see if that tells us something new. Do I know what that digit is now? Probably somehow, I don't know. Maybe I've got to do the diagonals actually. Oh, there's a 6 on this diagonal, so that's a 1. Right. Oh, so it doesn't really... Does it tell us anything? I don't know actually. I'm not sure that it does. We've got what? Oh, I see. So I've got the 2 extreme sequences. We knew there were 2 extreme sequences on the Ren bands around the Fistemfell ring. There was going to be a 9, 8, 7, 6, 5 pentomino, and there was going to be a 1, 2, 3, 4, 5 pentomino, and we've got those now. So the other bits and pieces here have to fill... Oh, this weather, look, it's going crazy again. We have to fill these with... well, I want to say they've got to be duplicates of these digits, don't they? There's got to be 1 more 2, 1 more 3, 1 more 4, 1 more 6, 1 more 7, 1 more 8. Well, that can't be a 6, 7 or an 8, so that is a 2. It's not a 3. That's a 2 or a 4. It's not a 2. Right, sorry, that's just a naked single again. That's a 4. So can I do the same trick with that one then? This digit has to be 2, 3, 4, can't be, or 6, 7 and 8, and it sees, so yeah, that's a 6. So 5 is over here in one of those squares, 5 is in one of these squares, by Sudoku that is. If this has got 5 and 6 on it, can it have 2? No, that can't. Ooh, actually, that's a 4. That is a 4, that's beautiful. That is a 4 because of this given 4. If that wasn't a 4, there would need to be a 4 on this sequence because it has 6 on it. And if this was lower than 4, there must be a 4 somewhere on it to be consecutive, and there couldn't be. So that can only be 4. So that's 4, that's 2, that's 3. This is no, I'm not going to say what I was about to say. That would be a ludicrous thing to say. Oh, look, now I want to pencil mark. There's a 3 up here. But can I make do without the... I think I can. I think we know now what we're doing, don't we? So I'm going to risk removing that so I can put my 3 pencil mark up here. Yeah. And actually that's worth it because now the 3 in row 3 has to be over there. Alright, maybe it wasn't completely worth it, but it was something. Now... Well, okay, right. There has to be another 3, doesn't there, on the Fistemfell ring. There's 1 here, but there are 2 3s in the Mahjong pieces, and there can't be a 3 here. So there must be a 3 here, I think. And now this digit is in a sequence, so that's 2 or 7. It's not 7, there's a 7 looking at it, so that's a 2. So we now need... Oh, we've got 2 6s on it, so this is a 7 8 pair and there's a 7 here, so this is all filled in. That's a 7 and an 8. And now we should have 2 of every digit on the Fistemfell ring, I think. And this needs to be a sequence, so that's got to be a 6. And there's a 7 at the bottom, so the 7 and 8 are... this is just wonderful. That's given me that digit, look. That's given me that digit just by a process of a little known logical deduction called Sudoku. Don't tend to use it very much, but I have used it there. Where's 4 in this box? There is where it is by Sudoku. So I can probably get this digit by the same sort of trickery. I'm guessing that's going to be a 6, and it is, because there's a 6 on the diagonal. So there's some profound symmetry going on. And these squares in the corners of box 5 are 1, 2, 8, and 9. Those are not 9 or 1, because there's a 1, 9 pair looking at them. So these are now not 2, 8. So these are a 1, 9. Oh, we could have got that anyway. Didn't see that. All right, what do we need in row 5 now? 1 and 9. Bother. What do we need in... It's not quite the same, is it? So in this column we need 6 and 9. Okay, well that's useful. There's a 6, 9 pair in this row, so that's become a 7. That's a 6. So that's a 6 and that's a 9. So that's a 9 and that's a 6, and all of that gets... That's a 6 by Sudoku. Good grief. 6 is in one of those squares. 7, 8 is done in box 1 by this 7. The 8 and the 5 are done by this 8. And this is a 2, 3 pair. It's sort of filling itself in. That's a 1 by Sudoku. That's a 4. I'm not really having to do anything now. I think we've done all the thinking, haven't we? That's a 5. That's a 1. It's magnificent, this puzzle. 7, 8 down here. We can do that using this power of this 7. So these squares now are 5 and 9. This is 3, this is 2. So I now know what those digits are. They are 7 and 8, which we can do. That does the 8 and the 2 in the middle. And now... that's a 2 by Sudoku, which means that's a 6 by Sudoku, which means that's a 6 by Sudoku. This is a 1, 9 pair, which must be resolved somehow. I don't know how, though. That's a 4 by Sudoku. This column needs 1, 9, and 8, so that's a 1 or a 9. Oh, I thought we were going to get a deadly pattern there, which I was terrified about, but maybe we'll figure it out some other way. That's 8. That's going to be 7. This is going to be a 9. Right, so this is a 5, 9 pair. I don't know if we can resolve it, but this is a 1, 8 pair, which we can resolve. And that 1 is beautiful. That's going to do things. It's going to do more things. 9, 1, 1. Here we go. These squares are 2 and 3. Don't know if we can do that. These squares are something and 3, 3 and 7. Yes, we can do that. Oh no, I didn't see that one. It's not 3 and 7. It's 3 and 5. Okay, that's still good. Ah, don't want to do that. Go away. Oh God, can you hear the rain? Oh my goodness. 5, 3, 3, 2, 2 and something. 4. That is so special. What a puzzle that is. That is such a special puzzle. Blackjack fits, take a bow. I absolutely love that. It was quite theoretical at the start, but the logic is just so... It's beautiful the way it's sort of a whole series of very smooth questions, I suppose. You know, you start off, you realise, okay, now I've got to put some 1s and 9s in the Mahjong pieces. What does that mean? And then you can get that thing about the way that these always have to be extreme within their sequence. And then you could get that the 5s had to be extreme within the other sequences. So you've got the nature of everything. And once we had the nature of everything, we could just fill the puzzle in. It's brilliant, isn't it? Let me know in the comments how you got on. I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.